Alright, welcome back everybody. Today we're discussing the second of the stiffness methods, and this time we will be handling the flexural case. So we will be solving for beams, for their moments, for their forces, and for their deformations. To begin with, I'd like to draw a beam here. And suppose we have a beam that looks like this, and it has two rotational degrees of freedom at either end. This is the first one, and this is the second one. Because this is a 2-degree of freedom system, we get a local stiffness matrix that is 2 by 2. So we have Kij is equal to K11, K12, K21, and K22. So what does this all mean? It means that for a moment at degree of freedom I, due to a unit rotation and degree of freedom j, while 0 rotations at all the other degrees of freedom. That's what that means. So let's formulate this problem by looking at a simply supported beam. I'm going to need two beams. Here it is. And because they are simply supported, I'm going to have a pinned support on this side, a roller on the other. A pin on this side, and a roller on the other. Okay. So the first thing that I want to do is to introduce a unit rotation on the left side with an amplitude of 1 and no rotations on the second side. I'm going to fix the second side. This is what I would get. What I would have is a deformation that looks somewhat like this. It's me going up and back down. Kind of like that. And I will have resultant forces P1 and P2. In this example, P1 is going to equal 4EI over L. At the same time, P2 is going to equal to 2EI over L. Here, E means the elastic modulus, I means the moment of inertia, and length is L. Okay, let's do the same thing with the second beam. In the second beam, we let U1 equal to 0, and this time U2 is going to equal to 1. And so the deformation is going to look somewhat like that. We are going to go down and back up. And there will be forces P1 and P2. Notice that I'm rotating my beams counterclockwise. And when we formulate the local and global stiffness matrices, we need to continue on with this sign convention. Otherwise, things can easily go wrong, our calculations will be incorrect, forces will cancel each other out, and it will look ugly. So it's very important to maintain whatever orientation you formulate your matrices with. In this example, I will have P2 equaling 4EI over L, and P1 equaling 2EI over L. And so my local stiffness matrix for flexure, pure flexure, will be EI over L, 4, 2, 2, 4. And it's very easy to remember. And as soon as you practice enough, you will never forget this matrix. Okay, let us do an example now. With this example, we have a two-span beam that has 3 supports. There is a pin support at the left side. Here we go. There is a roller support in the middle. And there is a fixed support on the right side. And we are given the lengths L, L, and the properties EI and EI. And we have the nodes A, B, and C. And so what's happening to this beam is that there is an externally applied flexure or bending moment with a magnitude of M. So this is the kind of problem where we are going to be solving for deflections, but the values that we're going to get are parametric. We're going to be solving in terms of the variables M, EI, and L. So we're not going to have many numbers to deal with. So the questions that we need to address are the following. Find. The first one is the rotations. Okay, so we're interested in the rotations at the locations of the nodes. And that's really the valuable thing with this method, with the stiffness method. At any point you are interested in, you will just create a node at that point. So you can make a larger member into a smaller member, and you can obtain all the deformations and rotations at that location. And lastly, we're finding the reaction forces. Okay, so for element 1, this is element 1, and this is element 2. For element 1, I have a local stiffness matrix that has the following look. It's EI over L, 4, 2, 2, 4. And I know this is kind of a simple example, but this is really a learning example. This is to really support the learning process, and I will upload a lecture later on, probably lecture number 10, which will contain a more sophisticated example on the stiffness method. And the stiffness method is really valuable. That's why we're dedicating most of the time in this course for the stiffness method. So the next thing we have to find out is the global stiffness matrix. So I'm going to redraw my beam, and firstly draw my boundary conditions. So I have my pin support, I got the roller support, I got the fixed support, and then I want to draw my global degrees of freedom. So I got this one here and the second one here, 1 and 2. And really I can't move anywhere else. One thing that I'd like to highlight is that yes, you may be thinking that a roller can move in the horizontal direction, but because this is an introductory course and horizontal motion in a beam like this involves axial deformations, I'm going to be ignoring axial deformations just because this is an introductory course. And axial deformations tend to be small when you compare them to flexural deformations and rotations. Usually they end up in the order of 1/100th of all those other deformations. So I'm going to ignore those for the sake of this course. Okay, so let's erase that. Here we go. Okay, so our global stiffness matrix will be K global is equal to EI over L. So we need a 2 by 2 matrix because we have 2 global degrees of freedom. And let's see. In the first member, I got the following relevant degrees of freedom. I got 1, 2, 1, 2. Because when I draw my local element and I overlap the global degrees of freedom on my local element, I get 1 and I get 2. Okay, so let's put those in. We got 4, 2, 2, and 4. And then I want to do the same thing with the second element. With the second element, only the second global degree of freedom overlaps, and it overlaps with the first degree of freedom. So what I get is 0, excuse me, I get 2, 0, 2, 0. So this is the only element that will end up in my global matrix, whereas in the first case, the entire matrix ended up there. So I get a plus 4. Okay? And actually, this should be plus 4 because it's 1, 2, 1, 2. So the 2 needs to go in the second index. Okay, so the next thing I want to do is to ensure that I've done everything correctly, which appears that I have. And what I need to do is to really wrap up this matrix, and I should have a matrix that looks like 4, 2, 2, and 8. Okay, perfect. All right, now I want to apply my forces, invert my matrices, and obtain my deformations. So I got K global times the deformation is equal to the forces. In this case, because I have moments instead of forces, of course my deformations are just going to be rotations. So I got 4, 2, 2, and 8. And I have U1 and U2. And this is going to equal to M and 0. Let's draw a better 0. There we go. Okay, so the first thing we got to do is to really invert a 2 by 2 matrix, and that's kind of tricky. We have to remember to calculate the determinant of this matrix. So we got 4 times 8, 32, minus 2 times 2, so minus 4, and then we've got to change the signs of the diagonals, so minus 2 and minus 2, and change the position of the other diagonal. So we got 8 and 4. It's okay if you don't remember this. This is a fairly straightforward process that we sometimes need to remind ourselves of. So we get the following deformations: L, 14 EI, 4M, and minus M. Oops. Let's draw better lines. Okay, and I'm going to try to be as neat as I can be. So what I want to do now is to draw my beam again, and this time I want my beam to be deformed. So here it is. This is the double span beam, and the first thing I'm going to do is to draw the boundary conditions. Here it is. And what I want to do now is to draw the deformations. So if I'm looking at my calculated deformations, I got a positive deformation, and we said positive is counterclockwise. And I'm looking at the magnitudes, and the first one is 4 times the other one. So I'm going to draw a deformation that is truly representative of that magnitude. It's kind of, so that'll be a 4, and this one will be tinier, so that's going to be 1/4 the other one, and it's in the negative direction, so it's rotated rotated clockwise. Okay, so let's draw our deformations. So we have our beam moving up, going down, down. Oops, appears that I've made a mistake here. Here we go, that's a much better line. And the position of the fixed boundary condition is always fixed, so no deformations in any way, no displacements, deflections, rotations, anything like that. So from this downwards position, we gotta go back up. Let's try again. All right, that's what it's gonna look like. And this angle here is 4m L over 14 EI, and this angle over here is going to equal minus m L 14 EI. And that's what we have. The second question that was asked of us is, okay, so what are the bending moment and the shear force values? Okay, let's do that. So we're doing part B. So if I went back to page 1, I should probably label this as part A, and so now we're moving to part B. Okay, so for member 1, I got P1 is equal to K1 times U1. If you recall, K1 was equal to EI over L, and the classic 4-2-2-4. That's K1. And then I know my deformations at that beam and that local element, and I have L, 14 EI, 4m, and minus m. And if I do the math correctly, hopefully I'll get something like this. I'll get m 2m over 7. And for P2, I have K2, U2. K2 is, again, the classic 4-2-2-4. And I got minus ML, 14 EI, and I got a 0. That's the fixed end. Okay, so what does this give us? We get 2 over 7m. Oops. 2 over 7m, and minus 1 over 7m. So if I drew free body diagrams of my local elements, I would have the following condition. So I got a beam that looks like that, and the second one that looks like that. And this time I'm going to draw my forces at the ends of these beams. So I got an M here from over here, and then I got a 2 over 7m. The adjacent location will be in the inverse direction, so 2 over 7m, that's clockwise. And lastly, the fixed support will have m over 7. So one way of finding out whether you've done your math correctly is checking to see if the two sides of the same node have equal and opposite signs, as we can see here. Kind of like that. Okay, so if I know that m plus 2 over 7m are in the same directions, so we are adding them, I can say that I got this V1, that's a V1 that's counteracting, there we go, that's another V1, that's counteracting the moment. So these are shear forces that are counteracting the moment, and we got V1 length L. And V1 is going to equal 9 over 7 m over L. Here we go. At the same time, I got a V2 going down here and a V2 going up here. And really that just adds up to V2L, L being this length here, is equal to 2 over 7m plus m over 7. And the V2 is equal to 3m over 7L. Here we go. And the next thing I want to do is to draw my shear force and bending moment diagrams per the question. So I got the VFD here. This is the VFD, and I also have the BMD here. Let's draw the BMD. That's the BMD. Okay, so from my calculations, I had shear force going up, and with shear force, it doesn't matter if it's going up or down. It's always the material or the section will always experience the same shear force, so it doesn't matter if it's going up or down. And then we got it going down, going to the right, and that's it. And we got the values 9 over 7 ml, and we got here 3m over 7l. And you can put any kind of patterns you're comfortable with to indicate that this is a shear force diagram. And yeah, that's it. That's our VFD. And as for the BMD, we have the following situation. Kind of like that, and like this. So down here we have a value of m. From the deformation diagram, we have compression here. Compression, this value is 2 over 7m, and this value is m over 7. And we got compression. And you can kind of really go back and see that, yes, in fact, at the location of the externally applied moment, I had a value of m. And in my BMD, I have a value of m at that location. So that's kind of confirmation that I've done all the math correctly and everything's looking good. So anytime you've done your math correctly, things are just going to work out. And next up, we're going to do the reaction forces. The reaction forces are really simple because they simply correspond to the values that we see with the bending moment, with the shear force diagram. And that's what I'd like to highlight now. So let me draw a pin support, a roller support, and a fixed support here as prescribed by the question. And now I'm going to draw my reaction forces. If I look at the shear force diagram, I'll have a force of magnitude 9 over 7 m over L here. It's very straightforward. If I look at the vertical drop in my shear force diagram, so if I go from this location all the way down to this location, I'll have a force going down. So that's 12 over 7 m over L. And lastly, I can look at this vertical increase. So we're going up. And I can simply apply 3m over 7l. And lastly, I want to look at my bending moment diagram. So I want to keep this in mind, this vertical in mind. So I have a fixed end moment reaction of m over 7. Okay, so that was it. That was a simple example involving the stiffness method for flexural elements. In the next lecture, we're going to talk about the flexibility method, which is the inverse of the stiffness method. And in the final lecture, we'll do a more advanced example. What I'd like to do is to run an experiment for you here in the lab that I work at, and to obtain some important stiffness properties from a real specimen. And so you would be able to see how you can obtain the stiffness matrix from a real physical specimen using actuators and load cells and whatnot. Okay, I appreciate you being here. Hope you learned. I'll see you next time.